All right, how's it going, everybody? It is Thursday, January 21st. We're going to take a look at section 1.3 today, associated with this is our first section associated with week two of the class here. And today, what we're going to look at is slope fields. Today, or this week, we're going to cover sections 1.3 and 1.4. So we'll hit up section 1.4 in the video that I'll make tomorrow. And that will deal with existence and uniqueness. These are two kind of important but topics that we're going to cover here that are going to kind of follow us all semester. These are going to be things that are going to kind of come up over and over and over again. So these are kind of important here. I don't think the content in either of these two sections is too terribly difficult, but it is like really important. Kind of like I said, it's going to follow us all semester. So these two topics of this week are pretty important here. So last week, what we talked about is kind of the fact that like when we're trying to solve differential equations, if our goal to understanding a system is to solve the relevant differential equation, because solving differential equations seems to require integration, which by the way won't always be true, very interestingly. What that means that like integration is hard, so like we can't really rely on our ability to solve differential equations because trusting that you're going to be able to integrate an arbitrary quantity. I mean, again, the big lesson from 50B Calc 2 is you can't integrate most stuff. And even if you can, it's hard, right? So the bottom line is we don't want to rely on finding analytic solutions. So analytic solutions meaning you can write a closed form equation, a y equals equation that directly explicitly describes the solution. It's not reasonable that we think that there's going to be necessarily an analytic technique that's going to handle everything for us. So what we want to do today is we want to look at a graphical tool to help us understand differential equations today. And what we're going to see is that drawing these graphs is kind of painstaking here. It's going to take some time and some effort instead of, this isn't just like flop a parabola out on the page. This is going to take like there's more time than that. There's no quick way to do this. So drawing intricate graphs by hand is not what we want to be doing all the time. So one thing we want to do is we want to ask ourselves as we're kind of going through this today, does it seem like there's going to be any way to take any graphical shortcuts? Hey, a friendly cat, how's it going? And that's going to be our topic of section 1.5 is going to be sort of a graphical shortcut we can take. And the other idea of today, number two there, is we want to use technology to help make these graphs for us. So really today, kind of one of the important, like half of today's video is sort of going to be us talking through some of the technology things that we want to have available to us. We're going to look both at how do we use technology to just get solutions to differential equations for us, and how do we know this is differential equations class here. I wish there was pizza and problems that was online somehow. And the other thing we'll look at is how do we get, where can we find something that will graph these slope fields that we're talking about here today. This is sort of a weird graph that we're producing here. So what I want to start with is sort of the lame thing here, which is let's start by drawing one by hand. And this is, I don't know, I'll probably ask you to draw one or two more by hand, but this isn't going to be necessarily a typical thing. But it's really important to do it once to see like where things actually come from, so that when you're looking at the technology produced graphs, you understand exactly how that graph was generated. All right. So drawing a slope field by hand, this will be our first example. And in fact, we'll follow this example for like a while today. The key to drawing a slope field is to understand that for any differential equation dy dt equals f of ty, the solution that's going to pass through some location in the plane, remember we're looking at a ty plane here, not an xy. Generally call it ty because time is almost always our independent variable when we're talking differential equations here. So we're in the ty plane, and what we want to see is that as any curve passes through any point ty, it's got some slope. And all we're going to do is imagine just a tiny little piece of a tangent line on all these solution curves that are out there. And we're going to draw just that little piece of tangent line there. So to graph a slope field, we're going to make a grid of small straight line pieces, right? They're all just going to be tiny little short pieces of what would otherwise be a general tangent line to a particular solution curve. And those are going to approximate what the solution should look like as it passes through that point. Right? So what we're going to do is we're going to make a grid of little pieces of line. So what I'm going to suggest we should do here is let's draw the slope field. I'm giving you a differential equation. I'm saying to you that I want t and y to both live between -2 and 2. and I want them both to be an element of the set of the integers. So this means -2, -1, 0, 1, 2 are the 5 values that both t and y want to take on. So that's going to make us a 5 by 5 grid, so 25 different slopes that we want to be able to identify here. All right. So the obnoxious part about this, right, and this is again me saying here, and I'm just going to highlight it. There we go. That sentence. I truly do believe that, but we're going to do it now. We're going to do the painstaking work at least one time so that we get the feel for what's happening here. So at these 25 different locations in a grid centered around the origin right there, we are going to identify what should the slope be of a solution curve that passes through that point. And we're going to draw a little piece of slope that will be representative of the slope that we have determined. And notice exactly what a differential equation is it is an equation that tells you specifically how to compute the slope at a point, right? So if I know some ty point in space, I can plug t and y into the expression on the right, and exactly what it's telling me is how y changes with respect to t. That's literally the slope of the curve at that point right there. So what derivative is the slope. So what a differential equation is, an equation that we can use to compute the slope of a curve at any point on that curve, knowing the ty location on that point. So we need to compute 25 slopes, and then we want to graph a small line with that slope on the 25 points. So what I've pre-set up for myself here is a table that we can go ahead and fill out with these values, right? So our goal is to get 25 values, all the combinations from -2 to +2 for t and y for their integer values. Then we'll identify their associated slopes right here. So kind of just what I'm thinking to myself is I want to fill these in with what I know I want these all to be here. So I'm thinking to myself, this is just going to be easier if I'm not in math mode for this guy. Get on math mode. There we go. So I'm thinking like -2, -2, -2, -1 is a point, -2, 0 is a point. And I know there's going to be 5 different -2's that we want there, right? So that's a 0, it's a 1, and that's a 2. And so I'm going to build all my inputs. My inputs here are t and y. My output is the slope at t and y. That's f of ty. That's our differential equation expression right there. So this is going to be like our leftmost column. All the t values are -2, all the associated y values. And then we're going to similarly get so there's all my -1s for t. There's 5 of them. And then wait, am I one short right here? Oh, I am. It's 8 by 3, so I've only got 24. I'll tack on one more at the very bottom down there. That's okay. So again, it's my grid of inputs. And then again, I'm sure I'm missing one. I'll tack that on in the corner down there. So our intention was to use this differential equation to compute what the slope should be at all those. I've identified 24 points so far with the 25th one in there. dy dt equals y minus t. So I'm thinking to myself, we've got here dy dt equals y minus t. And that's what I'm calling f of t y. So this should be pretty easy. We're just doing y minus t. -2 minus -2 is going to be 0. -1 minus -2 is going to be 1. 0 minus -2 is 2. I can see my pattern here. I think that's going to be my first row of them. Now I'm noticing that my t value changed, so I'm going to stop and think again. -2 minus -1 is going to be -1. -1 minus -1 is going to be 0. 0 minus -1 is 1. And then a 2, and then a 3. Next one up, -2 minus 0 is -2. And I think I can see my pattern that I'm watching come out right here. Again, down at the bottom here, kind of verifying that I'm not doing anything crazy. Y minus t, 2 minus 0 is 2. I'm all good. Continuing going here, I'm seeing my pattern is that I'm starting at a new one lower negative each time. This one started at 0, this one started at -1, this one starts at -2, this one's going to be my -3, because that's -2 minus 1, and -2, -1, 0, 1. because 2 minus 1 is 1. And finally, -4, -3, -2, -1, and 0, because I'm going to do 2, 2 is my last one that's sitting down there. Right? So what I just did real quick is I just did 5 little mental math subtractions to compute 25 slopes of lines, right? So this is like what the slope of a tangent line would be to a particular solution that passes through these. But one of the really important things I think you guys should be noticing about this differential equation that I guess I probably should have mentioned before is notice that this is not separable. So far, the only technique that we have for solving differential equations analytically is separation of variables, but that requires us to be able to separate y and t by multiplication, which we can't do. We can only separate them by subtraction. So currently, you don't know a technique that's going to do this for us. And in fact, the technique for this one, we're going to get in section 1.7. Where we're going to talk about linear differential equations. You should notice that this is linear in terms of y. There's a single y, there's y to the first power right here with an additional term of t out there on the end. So in 1.7, we'll be able to solve this one. We'll have technology produce this solution for us here today, and we'll verify it. So what we want to do is we want to take all these little chunks of slopes that we just identified over here, and we want to, and we want to graph a little piece of line that's got that slope on each of the locations in the grid. You should notice my grid goes from -2 to 2 in both dimensions right there. So this is exactly where I wanted to be right here. So again, this is our t-axis. This is our y-axis here. So we can go ahead and do this. So at -2, -2, that's at my location that's right down here. Our first slope is 0. So I'm going to draw a tiny smidge of line that has slope 0. So there we go. There's our first piece of our slope field right there. A slope 0 line at -2, -2. Now at -2, -1, -2, -1, that's sitting right here. We now should have a slope of 1. So there's my line of slope 1. Then we're going to get slopes of 2, 3, and 4 as we move up this column. So it's going to get a little steeper, and a little steeper, and a little steeper. By the way, you should be immediately noticing if I said to you, hey, draw a line of slope 4, and then somebody else draw a line of slope 5. It's really hard to eyeball those things, so I think that we can all see that I'm getting steeper here, but these are certainly kind of a visual estimate of the slope in a sense right there. I've got the exact slopes up in the table. So that's our first 5 right there. Now at the point, why is that thing not centered there? That's weird. Doing some weird things to me in this table. Anyway, -1, -2. So -1, -2 is sitting down here. And I'm noticing that we actually have a slope of -1 at that location. We have a slope of 0 at -1, -1. So I'll draw a line of slope 0 there. And then we have slopes of +1, 2, and 3 as we continue up the line right here. So that looks like that horizontal, or that 45-degree angle line. And then we get steeper and steeper right there. Okay, those are kind of steeper and steeper. That's okay. Carrying on. Now we want our t equal to 0 line right here. So that's these 5 guys right here. We're going to start down here at this -2 slope, so a pretty steep negative slope. Then our slope of -1. Then our slope of 0 at the origin, right? 0 minus 0 gave us a slope of 0. Then our slope of +1. And then our slope of +2 right there. Again, I'm just reading off the slopes that I see that I have computed for myself in the table and the point in space at which I should be drawing that associated slope. So again, at the point t equals 0, y equals 2, that's at this location right here. And at this location, I drew a small piece of line with slope 2 as we computed the slope of that line to be. So cruising along here, 1, -2, I've got this very steep -3, and then a -2, and then a -1, and then a slope of 0, and then a slope of +1. And finally, over here, when t is +2, I'm going to get this very steep negative right here, a -4 slope, and then a -3 slope, and then a -2 slope, and then a -1 slope, and then a 0 slope right here. So there we go. So what we just did is we just drew a slope field that is associated with the differential equation dy dt equals y minus t, right? It was y minus t, not t minus y. Yeah. So here's some things that I can sort of see now. And again, here's the deal. One way that we might analyze this differential equation would be to find its solution, but you guys don't know how to do that till we get to section 1.7. But I still might want to answer questions such as, if a point has an initial condition of, maybe I should just kind of type these out real quick right here. Let's say this. Um, now I'm screwing up. So here's the deal. One piece of information perhaps I am interested in is saying, hey, listen, if I'm given initial conditions of 1, -1, what's going to be the long-term behavior of that solution? The problem for you is that because you don't know how to solve this differential equation, you don't have any way to like compute that answer, right? You don't have an equation to which you can just take a limit as t goes to infinity to determine it. Right? But now that we've drawn the slope field, I feel like I can answer this question. It seems to me like I can see what the shape of my solutions look like. And even though I don't know their equation, I kind of have a good estimate for what the graph is going to look like, right? So what I'm going to do is I'm going to draw this guy right here. And I'll underline that guy in green. 1, -1 is at this point that's right here. And what I can kind of see is it seems like this thing is going to be taking a downward trajectory this way. And it seems like where this is going to have come from is it seems like there's going to be some increase here. It seems like it should be hitting a slope of 0 when it's on the line, that y equals t line. And then it seems like, I don't know, it's got to be kind of like matching up with these sort of straight line pieces that are out here, right? So it seems to me like I could say it looks like we're going to have y is going to go to negative infinity down there. I can see that as t gets bigger and bigger and bigger, just based on my slope field, I can see that y is going to tend off towards negative infinity right there. So notice that what this slope field is doing is it's allowing us to make long-term predictions about a differential equation without ever actually solving it. Right? We didn't come up with a solution for this, but visually looking at the slope field, I can get a sense for what our solutions look like. Now, one of the questions I might ask myself is, do you know the equation of this green curve right here? And my problem is that I don't. It doesn't look like anything that I recognize, especially if it's going to get like asymptotically close to this y equals t plus 1 line right here. That seems sort of like I don't know what the equation is, unfortunately, but I know what its shape looks like because I can just draw some pieces. So this is sort of our version of like, when you're in like early algebra and it's like, hey, graph this equation. And because you haven't been around in algebra for long enough yet, you don't know like what cubics look like or something. Well, the lame way to graph any function is just to plot a bunch of points and then draw a curve through it and you're good, right? This is sort of like the graduated version of that. Instead of having a y equals equation and plotting points, we have a dy dt equals equation and we're plotting slopes, right? That's the sort of stepped up version now of just, I don't know, plot a bunch of points and draw a curve through it. Now we plotted a bunch of slopes and drew a curve through it right there. This is the calculus version of the lame version of graphing. But here it's not lame. It's not lame that we can't do integration. Integration is just really hard, so we don't ever expect to be able to find these solutions necessarily. So slope fields, hugely beneficial. They say to you, you don't need to know the equation of the curve to still know what the curve is going to look like by finding some slope estimates in the region of interest and drawing a curve that agrees with them. So I want to do 2 more questions like this one that I just asked right here. So I'm not just copying this, obviously. And instead, maybe we ask ourselves what's going on with a point that maybe starts at -1, 1. I don't know. Let's just switch the negative sign right there. So let's switch our color here and look at this one. And then I'm going to ask one more. That's a very important one. So I'm going to go and let's change our color here. Do another. So if I start at -1, 1, that's this guy right here. And again, it looks to me that if we go backwards in time, I should be exactly following the trajectory of that piece of slope, but it looks like our slope is going to like flatten out that way. And it looks like my slope is just going to get steeper and steeper and steeper. So in this case, and this guy right here, if we're doing this one in red, it looks like our y values are going to tend off towards positive infinity. So again, I can make predictions about the long-term behavior of a particular solution associated with a specific initial condition, not by solving and taking a limit, but rather by graphing and visually inspecting the graph. Right? Last one that I want to ask about is, what if we start here? Now again, hold on, before I go on again, I want to say to you, do you know the equation of this red curve that I just drew here? Because if you did, then I'd know a general solution to this differential equation. And no, I don't, because I don't know anything that like grows like this but gets asymptotically close to this y equals t plus 1 line right there. Right? But if I ask this one now, what's the long-term behavior of a solution with an initial condition negative 1, 0? Well, negative 1, 0, what does it look like is actually happening with this guy here? Let me change my color one more time. It looks to me like if we were to start at negative 1, 0, well, this says to me that my slope should be positive 1. And I don't really see any reason why it should ever differ from that. It's just going to be a slope of positive 1 until we get to another point where it just says, yeah, slope's still positive 1. And slope's still positive 1. It looks to me like this is also a solution to the differential equation. And now I say to you, do you know the equation of that line? And the answer is yes in this case right here. Yeah, an oblique asymptote. Good call. And so, super importantly, right here. Oh yeah, and so if we started. Oh, so good question. So I'm going to say two things about what I see in chat right here. One is saying it looks like an oblique asymptote, and I am exactly into that right there. Now, one of the questions you should be asking yourself is, are you sure that this like green line and this red line never cross the purple line? It turns out, although it's not obvious by the section title, that section 1.4, existence and uniqueness, is very specifically what we're going to be discussing, is exactly that. And I'm embarrassed right now. I just glanced up there and I saw I gotta fix that. I can't look at that typo here. Existence is not with an A, it's with an E right there. Okay, so it turns out that's exactly going to be our topic of discussion next class, is saying, do you think that that trajectory maybe at some point crosses the purple one or not, and why not? That's exactly going to be our section 1.4 topic of discussion right there. So it does look like, it seems like those other solutions are asymptotically being approached, but they're not horizontal or vertical, the line, it's an oblique asymptote right there. The other statement I'm seeing here is, what about at ty equals 0, 0? Well, the thing I'm kind of picturing to myself is that at 0, 0, it seems like we should have a slope of 0. So as I begin exiting the point 0, 0, we should be going like flat, either to the left or to the right. Backwards time to the left, forwards time to the right. But what I can see is that the more I move to the right, I'm sort of picturing what my slope line chunks look like at not just our interval or our integer locations, right? We could have done this every tenth of an integer rather than every integer. We just get a lot more finer resolution as to what our slopes look like. And what I can kind of see happening here is I'm certainly expecting that our slopes should be starting to get negative there, right? So I think that if we were going to go through 0, 0, it would be very similarly matching this green curve right here, just raised up a little bit, but I think otherwise it would be a pretty similar looking curve right there. And so kind of intuiting to yourself, what do my slope line chunks look like between the ones that I've graphed, is sort of helpful in you kind of justifying this to yourself as to what this looks like. And again, this is in a sense like a graphical approximation right here. But the other thing that's really nice is that we're not going to just do this by hand. We're going to let technology help us out with some of these things as well. So like we won't necessarily do this a bunch. But again, what I can see is any curve that agrees with all these slope lines right here is a particular solution that's associated with this graph. we can visually see one of them that we actually know. Out of all of the different infinite number of curves that I could draw on this plane that are going to agree with our slope field lines, one of them looks like it should be a linear equation. And I know the solution to that one, right? That's y equals t plus 1, a slope of positive 1, a y-intercept of positive 1. So there's my equation. So I'm thinking, I feel like this should be a solution to this differential equation right here. I don't think it's the general solution because I see I do get some curved solutions out here. So the general solution shouldn't necessarily be linear, but it seems like one case of the general solution should pan out to be linear. So that's sort of something I'm expecting to kind of see come up right here. And by the way, I'm going to verify this in a second. So we notice that this is inseparable. We don't have a technique to solve it yet, but by graphing the slope field and imagining solution curves, can we see a possible solution? Yeah, that's exactly the y equals t plus 1 that we just grabbed right here. So let's go ahead and verify this. Verify this is a solution. We couldn't have come up with this on our own. I don't think I was just going to think about it and get to there. But now that I think I've found it graphically, we can use the differential equation to verify. I'm just going to substitute in t plus 1. The derivative of t plus 1 is 1. T plus 1 minus t is 1. So yeah, it looks like y equals t plus 1. Since we were indicated to think of it by the graph, we verified it with the differential equation. I now know for a fact that y equals t plus 1 is a particular solution to this differential equation. It was going to be really hard for me to come up with that without a graph, considering we don't know an analytic technique yet, right? So this is using the graphs. We can use the graphs to help us identify maybe some of the easier solutions that are out there to kind of help us out with some of these things. So we'll see other types of solutions that we can visually identify as well with our graphs coming up here in a minute. So let's take a pause from doing some math for a minute, and I want to take a lap around some of the technology things we're going to be using this semester. There's going to be two broad categories of technology usage that we want to be comfortable with this semester. One thing we want to do is to be able to have technology produce exactly this graph for us, and we're going to see several different versions of that right now. I'm going to go to show you 3 different resources that we can use to produce this graph. But another thing that I think that I would like us to be able to do is to just literally ask, a computer, what is the solution here? We don't know what the solution is yet until we get to section 1.7. So I don't want to wait 2.5 weeks for that guy. I would rather just go to something on my computer and say, computer, tell me the solution to this differential equation. I would like it to tell me that. I hope that you are not going to be terribly surprised to hear that that is hard for computers to do. It's not necessarily simple to find differential equation solvers out there. So let's talk about this stuff. Turns out that graphing slope fields and their particular solutions is relatively computationally expensive. When I say computationally expensive, what I mean is it takes a lot of multiplication and addition and subtraction to make this happen, like lots and lots and lots of it. The more precise we want it to be, the more computation is required. Right? The other thing is that symbolically solving differential equations, like giving it t's and y's and expecting back t's and y's, it's very technologically, I'm just going to say it's difficult. It's hard to write programs that are competent at handling like variables rather than quantities. What this means is that the number of tech tools that are out there for our purposes are relatively small, and the good ones cost money because they take a lot of really smart people to build. So let's again talk about these two things. Our two goals are have technology actually produce equations for us, the solutions, as well as have technology produce graphs for us, a visual representation. So let's talk about both of these things here. So solving ordinary differential equations. So by the way, ODEs is like another shorthand abbreviation that people will often use for this class, because in this class we never talk about PDEs, partial differential equations. So if you're like at a college that offers PDEs, which we do not at College of the Redwoods, it's common to make that distinction. ODEs, PDEs. That's sort of like the introductory differential equations, the advanced differential equations, ordinary and partial. So that's just another shorthand that's pretty typically representative of what we do in this class. So ODEs, solving ODEs with technology. This just isn't easy. I honestly don't know how. All right, here's an abbreviation for you. CASs do this. A CAS is a computer algebra system. And basically, it's pretty easy for us to use computers to do things like manage variables. Like if I said x is 7 and y is 3, add x plus y, it will do 7 plus 3, it'll tell me 10. That's not a problem. Getting computers to actually understand them as just variables, that x plus y is just the expression x plus y, that is higher level stuff. Oh yeah, so the TI Inspires have CASs now, and so like my biggest complaint about TI calculators is that they haven't changed their technology in like 30 years. Well, finally now, after 30 years of work, they actually can handle some symbolic manipulation stuff in there, and that's like relatively new for even TI calculators to be able to do that. And I guess I don't know about that. I don't think that the TI Inspires can solve differential equations, but I certainly don't know. But I'm going to show you a way that we can do this now anyway, since I'm assuming none of us have TI Inspire, few of us have TI Inspires. So the bottom line is that there is one very good source for doing this. It's called Mathematica, if you're not already familiar with Mathematica. Unfortunately, Mathematica costs a whole lot of money. And so I certainly don't expect us all to go purchase Mathematica just so we can check our answers this semester. So I'm going to show you a way that we can do this in Python instead. And I'm going to talk about the pros and cons here, and I'm going to say the cons first. The cons of using Python to do this, relative to Mathematica at least, is that it's a bit clunkier in that in Mathematica, I can give like one line of code, and it's like, yep, here's the solution to the differential equation. Whereas in Python, we'll need to, in a sense, do like a little bit more like setup. It's still going to be relatively easy, but it's Mathematica is like built to do smart math things, whereas Python is more of a general purpose language. So it's not like specifically made to do math. So it will take a little bit more code, but it's still nothing crazy out there. The other thing that's true is that Mathematica is a gigantic beast of mathematical ability. Mathematica can handle like a huge variety of different differential equations. It can handle partial differential equations. It can handle first order, second order, third order, fourth order. It can handle systems of differential equations, all this stuff. Python has a bit more of a limited scope of the classes of differential equations that it can manageably solve. By the way, I keep on saying Python, but it's not Python broadly. It's the one specific library of Python content that we're going to use. But anyway, the point is, Mathematica is incredibly robust with this. It can do a ton of stuff. Python can handle a smaller set of cases, but it's really going to handle most of the cases that we're interested in this semester. So that's good for us for now, at least. The good part about doing this with Python is that Python's free and that we're going to be using Python for our unit on numerical analysis. So our question right here, a very good one. What if you have almost 0% computer experience? I'm definitely anticipating when I teach these Python topics, I absolutely expect that nobody has any coding experience whatsoever. One of the reasons why Python is a very friendly language is because a lot of it is pretty intuitive. If you're used to typing in things in line in the calculator, and if you're used to function notation, then Python's going to match up with that pretty similarly. So I'm going to be giving you guys a lot of code that I'm just going to expect you to alter my code rather than come up with your own like original programs and stuff like that. And we'll see that more once we get into our programming unit. Today's stuff is going to be a little bit more like if you want this code, then it's straight up copy and paste, and all you have to alter is the equation being solved. Later, I'm going to expect a little bit of creativity from you, but it's still going to be, in a sense, like replicating something that you've already seen a chunk of. So this shouldn't be some crushing programming experience right here. This should be hopefully a pretty natural first look at. I expect this to be most people's first programming experience here. And so one thing I want to say to you is, unless you're on a machine where you cannot download and install Python, then you should probably do that now. You'll want to do this later for our numerical unit anyway. So I'm just thinking you might as well get ahead of that. So topic number one for technology today is let's real quick go and look and see where you can do that. So let me talk to you a little bit about Python. In general, for programming languages, people that are building a programming language don't want it to be some gigantic beast of a language where if you're ever going to write Python code, for example, you need to download some 12 gigabyte, language. That's burdensome. It's going to prevent the distribution of the language. It's going to make people not want to use it. So one important thing about Python is that its core is relatively small, and that's good and important for us. That's a smart move on Python's part. On the other hand, what that means is that Python at its core doesn't know like math stuff. For example, in pure Python only, there is not sine and cosine functions, right? There is not a square root function, although we do have exponentiation, so you can just do an exponential of 1/2 power, stuff like that. Natively, Python in its core doesn't know how to do things like produce graphs, right? But what people have done is they have written what are referred to as libraries or packages, which is a group of related content that does specialty jobs. So we are going to use today a package or a library called SymPy. And by the way, it's very common for people to force the letters PY into their package name to represent that it's part of Python. SymPy is supposed to stand for symbolic Python. It's going to do a lot of symbolic math manipulation for us that pure Python doesn't know how to do. So there's an external library called SymPy that we want access to that is sort of an addition in a sense onto Python. So one of the important things is that if you were to only download just Python and nothing else, then you technically don't still have enough to do what we're doing today. We also want that other library. So to that end, what we want is we don't just want to install Python. We're also going to want several other libraries that do other math jobs for us. We want SymPy to do symbolic stuff. Later, we're going to want NumPy to do numerical stuff in Python. Just that group of nerds chose that name. It's not anything like super special. That was just the name they chose. We're also later going to need a plotting library, and so we're going to bring that thing in. So rather than you guys having to screw around with like a different download every time we want to do something different with Python, there is a group of people that have collectively packaged up together Python with all of the most commonly used libraries, as well as some programs in which you can write code and run code, right? So this is like saying you learned English, but you don't have Microsoft Word. You still can't write a paper because you still need a program in which to write the language. So similarly, we need an editor in which we can write and run the code. So the Anaconda installation of Python is all three of those things. It's the core Python. It's like the 100 most commonly used libraries, and it's several options of editors with which to write and run code. And all of that will be piled into one download and installation so that you don't have to like think hard about this and deal with little ticky-tack stuff all the time. It's all there in one spot. So what I'm saying to you is I highly recommend the Anaconda installation of Python, but honestly, there's about a bajillion different ways to get this stuff on your computer. This is just the easiest one. This is a relatively large download because it is going to come with like 100 different libraries of content. So this is, I think it's like a 2 gig download or something like that. So it's kind of big, but it's not massive, and it will prevent you from having to screw around with stuff later. So this is by far the recommended thing. So I am just going to go to the site real quick. I'm gonna control click on this thing, and it's going to take me to the website, and I'll bring that up here. So here we are. This is what it just brought up to me. You can see that this is the Anaconda website. Python has grown in popularity significantly in the last several years, particularly due to its ability to handle lots of data science applications. So that's why it's referencing this right here. But if you scroll down, you can click the download button, and it just scrolls you down to the bottom where it's got your Anaconda installers. You guys are all on Windows, Mac, or Linux. All of you, if you're on, unless you're on like the literal oldest running computer on Earth, then you should all be in 64-bit. If you have like a truly ancient computer, it might be that you need the 32-bit. But you should all be 64-bit unless this is like your grandparents' laptop from before you were born kind of thing right there. Most all of you should be on 64-bit right there. So this is your easy, just click a button, download, install, that kind of stuff right there. And again, it's going to give you access to everything that we need. So there's one thing right there for us. So let's pop back over to Microsoft Word. So again, that link is available for you. Or like every time people ask me about this, I'm like, I don't know, just Google it. And all I ever throw into Google is just Python Anaconda install. Anaconda is the name of the overall collection of stuff. It's really all about Python, the programming language, and you want to get the installer for it right there. So real easy to Google for that and find it. So what I want to do as our first technology item for today is let's do a bare smidge of Python. And again, even if you don't do this right now, that's fine. You might want access to this right now so you can check some solutions. You're going to want Python later, so you kind of might as well do this. But if you don't do this week, that's not the end of the world right here. But I want to show you that we can get Python to do this for us here. So let's take a moment now. Let's come back. I want to know the general solution to this. We've so far found one particular solution out of an infinite number of solutions. We can see that there should be all these curvy solutions out there, tons of them. I want to know what the general solution is to this overall differential equation. Let's have SymPy do it for us here. So I'm going to step back over into my browser. And what I did yesterday is I wrote just a little bit of code that's required to do this for us here. So Jupyter Lab, that you can see at the top of my screen right here, is one of the possible editors that you can use to write and run Python. Jupyter, and you can see Jupyter spelled with a Y right there. Jupyter stands for Julia Python R. Those are three different, very math and statistics-based programming languages that are often used in data science. The Jupyter project, which created the Jupyter Lab and Jupyter Notebook structures to write within, was made with a very specific intention of sort of being a copycat for Mathematica. Mathematica kind of, although I have a bunch of problems with Mathematica aside from how expensive it is, the best part about Mathematica in my mind is the structure of writing code. It's not like you're just writing some gigantic program and running it. It sort of has this cell-based structure where it's in a sense more like paragraph by paragraph or idea by idea. I'm going to show you another cool part about it here in a second. So you can see I've got different cells that I'm writing code within. I just made the choice to make each of my cells one line of code only. It could easily be the case that all four of these lines of code are just in one cell. It would run just fine. But the nice part is you can kind of separate your ideas and run just a little bit of code at a time this way. And that's very convenient, especially for people that are new to programming here. So some nice things that we can do here. So I guess I'm going to talk about the code that I've written here, and then I'll show you guys some other cool features of Jupyter, and then we'll pop back into the Word document here. So one, the SymPy library is the thing that's going to know how to do things like understand equations algebraically, and it's got solving methods within them, some functions that do the solving for us. So my first line of code here is to say, bring in the knowledge associated with SymPy. It's going to look in my computer's file system, and it's going to look up the SymPy stuff, and it's going to sort of bring it into like it's Python's like awareness inside of this notebook right here. So I'm going to press Shift Enter. And you could see for a second there was an asterisk right there, a star, that meant it was thinking. Now there's a 1 there, meaning that's the first run cell in this notebook here. The first thing I'm going to want to do with my SymPy ideas is I'm going to say, hey SymPy, use your function that's called symbols to make the symbol t. This is going to take in what is known as a string, like a verbal representation, the letter t, and I'm going to save that as the variable in Python t. So the important thing that's going to happen here now is that in my notebook now, it now understands the standalone letter t to be a SymPy symbol, right? And so now what I can do, for example, is I can just say, hey Python, what's t? And it tells me, oh, it's t. That's what t is, it's t. As opposed to if I did something like saying x equals 3, notice that x equals 3 has nothing to do with SymPy. I'm not telling SymPy to do anything. This is just standard Python stuff. I could say, hey Python, x is 3. And then I can say to Python, hey, what's x? And it tells me it's 3. That's the more traditional way that a variable is stored in Python. So the special thing that SymPy is doing is it's storing t now as a symbol t that can be manipulated rather as a value like 3, which could be computed upon, right? That's the distinction that SymPy is making for us. Another thing that we want to define here is a function y, because y is a whole function of t. We don't know what y is yet, but I know that y is a function of t. It's not just another variable. I could have done up here, I could have defined y the same as I defined t, but I want SymPy to understand under the hood that y is a function of t. So I'm saying, hey SymPy, use your function, the name of this function is literally function, to make a function. I guess I'm calling it f right there, although I don't know that that actually matters right there. And here this says, and make it a function of t. That's our previously defined t right there, right? And I'm going to call that thing y. By the way, I really don't know that that f kind of matters at all right there. It's going to know t and y as my two symbolic variables, right? So I want to run this line of code here. So now it understands what y is. And by the way, I actually don't know what my output looks like for this. Let's see real quick. What does it say that y is? Ah, it says that it's a function of t. That's super cool right there. Okay, so I feel pretty good about what I've written so far. Y is a function of t, and SymPy within Python knows that. So now what I want to do is the ever so important step. So notice that these were our two setup steps right here. This is the step where I'm going to solve a differential equation, right? So now what I want to do is I want to solve this dy dt equals y minus t. Right? Now what I want to do here, and so I'm going to write some extra stuff in here to show you what's going on. Your question should be, what is this expression in the middle right here? And I'm going to show you why I have it written this way. So I'm going to say, hey, senpai, I want you to solve, but do a differential equation solver. That's what the D solve stands for, is differential right there, or derivative solve right there. What is this going to be? Well, y dot diff, this is going to say differentiate y. So this term right here, that's my dy dt. It's the differential of y. It's the derivative of y. Minus y plus t. Well, that's sort of strange. I notice I'm not giving it an equation. I gave it an expression, and I kind of lumped some stuff here together. So that's kind of strange, right? Let me show you what I did. And by way of showing you the math that I did to put that expression in there, I'm going to show you another feature of Jupyter along the way here. So one thing that's also cool is that instead of just writing code in Jupyter Notebook, it's also okay with me writing words. Notice that this currently says code up top. I can switch this to what's called Markdown, and this is just going to let me write some words in here, right? So it's just going to be some words. I could make a paragraph in there. Even better than that, I can write some fancy math formatted things in LaTeX if you're familiar with that. So here I'm going to type some stuff here, and then we'll talk our way through it. We want to solve the differential equation. And what I'm going to do is I'm going to type out that differential equation here, and I'm going to give it a little bit of LaTeX formatting here. LaTeX, all math stuff is going to go between dollar signs. So when I use those dollar signs, that says start math mode, and then the second dollar sign says end math mode to go back to just regular text. What do I want to do? Well, I want to write dy dt as a fraction. So I'm going to use the LaTeX command for a fraction. So it's /frac with some curly braces for dy as the numerator, and then another set of curly braces will give us the denominator. And I'll just run this real quick. You can see it does give us the nice dy dt fraction that we want right there. I want to keep going though. I want this to be equal to y minus t. So I can finish typing that right there. And now I have a nice math formatted expression for what I want this to look like. So what I'm going to do now is I'm going to say, to do this, first we homogenize. By which I mean we make it equal to 0, right? To homogenize an equation is to make it well mixed. So it's like mixing the two sides together. So that really means push all terms to one side so that the equation is equal to 0 equation. And so now I think this should be looking like dy dt. And all I'm doing is just subtracting over y and adding over t. And so now I think that I have homogenized my differential equation, right? I subtracted over y, I added over t. This expression that's on the left, the homogenized differential equation, the expression that is equal to 0, that is exactly what I am plopping on into the dsolve function that's sitting right there, right? The derivative of y. It knows y is a function of t, so I didn't even have to say take the derivative of y with respect to t. We defined y up above as being a function of t, so it already knew that part. So this is dy dt minus y plus t. It doesn't want to screw around with the whole equaling maybe something else, so it is the case that SymPy always wants a fully homogenized differential equation. So it's always looking for an expression that's equal to 0 with derivatives in it. And so what I can now finally go do is I'm going to run this line of code. I'm going to say, hey, SymPy, solve the differential equation that is this differential expression equal to 0. That's the implied behavior under the hood right there, right? So there's a little bit of knowledge that you have to have. That's not like something I would directly guess. But also if you just like Google like SymPy tutorial, it's like literally on page 2. It's going to show you like basically exact this. This is how I learned it. I just kind of Googled around for this stuff. It took me like 30, 45 minutes to get it my first time. I'm explaining it here in like 5 minutes. And even with, I think, no programming experience, you can see that if you want to do this for yourself, you copy this line exactly, you copy this line exactly, you copy this line exactly, and then down here, you just need to do a bare minimum amount of algebra to set that statement up right there, and you're going to be good to go. So let's run this and see what we see. So I'm going to run that, and it is giving me now a function of t as our solution, as it should. Notice we have a constant of integration like we expect. Oh my goodness, I see a t plus 1 in there. Remember that we just found y equals t plus 1? That completely seems believable to me as a part of our solution that we should have seen. That's one of our particular solutions. Although I gotta say, I got one little beef with this. Don't you feel like this is a super weird format for the equation to be written in? I feel like it's weird to have an e to the negative t right here when there's an e to the positive t on the outside. I kind of wish it would have multiplied this whole thing back out. So here's what I'm saying to you when I say a lot of things in Python, you can just guess what you want to do. I don't just want this expression. I want this expression multiplied out, also known as being expanded. So I'm just going to rerun this line of code now, or maybe I'll at least copy it down just so that we can see the comparison right here. And I'm going to say, so this code is equal to the equation. What I want to do is also apply the operation of expand. And that just multiplied it out for me right there. Oh, that's so cool right there. I get all excited when these things work out and they're so nicely formatted like this. Oh, and notice, like the way that this is written is literally formatted exactly the same as this. So SymPy's output, it literally gives a LaTeX style output so that it matches the equations that we can write up there. Oh, this is just so nice. This is just so nice. So the point to me is this. This is not a form of equation that I don't think you guys have seen before. We're adding linear components to exponential components right there. This is a sum of a linear equation and an exponential equation. But the point is, I now just got a computer to just solve this differential equation for me, which I believe to be pretty dang handy right there. You should notice that if C1 is equal to 0, then we get that particular solution of y equals t plus 1 that we previously identified from the graph right there. And yeah, and so I'm happy that you feel that way, friendly cat. This is not much, right? This is a few easy lines of code right there. We made a quick guess as to what we might do to make this look a little bit different right there, and it worked, right? And by the way, factor is another command. So I think if we did dot factor, it just gives, oh, it didn't like that right there. Oh, I think I see why, but that's kind of it. It's because expand is an equation right now instead of an expression. Whatever. The point is, if you were to just Google for SymPy stuff right there, it'll give you a whole list of math operations that you could apply. And since you know math, it's sort of intuitive as to maybe how you would use those things right there. So again, you've got some lines of code now that if you just want to download and install your Python and open up a Jupyter notebook, you can type exactly these things and you will get exactly this. And just real quick right there, I'm just going to bring this screen up one more time just in case this was some things you wanted to look at. This is an entirely different programming language in a sense. This is LaTeX, L-A-T-E-X. And this is, in a sense, a whole nother language, but this is a typesetting language to make fancy formatting things happen. Learning LaTeX is kind of really going, in a sense, above and beyond here. But also, if you think that you're going to be a legit math nerd in your life, this is what math nerds do to make their stuff look good. When I was in grad school and I was handwriting my homework, all the people that were smarter than me and had more time because they were spending only 10 hours on their homework instead of 15 hours like me, they were all writing up all their solutions in LaTeX because they were all badasses and I wasn't. At that time, I have since grown in my ability to at least make my work look good. So learning LaTeX is sort of one of those side things that it's what the smart people do to make sure they look as smart as they are. When you guys are in your fourth year at whatever four-year university you go to, and you're doing your senior seminar project, if you're a math major, an engineering major, a computer science major, you are going to learn LaTeX because that's how you're going to present your project officially right there. At my undergrad, it was right after I was done with my senior seminar that they started making it a requirement that you had to produce a fully LaTeX formatted document for your final paper submission and stuff like that. So very typical that you'll be expected to learn this type of formatting. But I also hope that this doesn't look like a too mind-blowing of a thing either. You also just have some like syntax to learn, like, oh, to make a fraction, you use /frac and use curly braces with LaTeX stuff. So this is another thing where I'm not going to talk a ton about like teaching the LaTeX stuff this semester, but I'm always going to introduce it because I'm always hopeful that people will kind of like, I don't know, get excited about it like I do and trying to figure it out on your own. And it's another one of those things where there are just infinite resources online to help you learn some LaTeX stuff like that. So certainly Google around for some stuff like that if it's something you're interested in. Try and mimic the things that I do. Try and guess things that you think might work to make things also better for you. But LaTeX is super cool, and it's super cool especially that it is automatically built in to Jupyter Lab rather than having to be some other extension you've got to work out yourself right there. So I'm going to wrap up our little Jupyter section right here to say we have now used this to solve something. So I think I got the solution of y equals c e to the t plus t plus 1. So let's pop back over into Microsoft Word here and play around with that for 1 second. So I'm going to do two things with this. One, let's verify that this is in fact a good general solution here. Now I'm going to go ahead and I'm going to plug it into both sides, right? I'm going to take my derivative of c e to the t plus t plus 1, and that should be equal to c e to the t plus t plus 1 minus t. Right? When I take my derivative over here, I'm just going to get c e to the t. That didn't change at all. Plus t becomes plus 1. Plus 1 goes to 0. So there's my derivative. On the right-hand side, t and t cancel, leaving me with c e to the t plus 1. So we could verify by hand that the solution that we got from SymPy was good. So that's a nice thing to see. The other thing I want to do just real quick, just to kind of make sure that we kind of see all this nice stuff coming together here, is that back here, we proposed this initial condition of -1, 0 when we arrived at what we believed to be this straight line solution that we thought we identified. So -1, 0. Let's apply that initial condition and solve for t. Initial condition -1, 0. That says y is going to be 0. C E. Oh wait, it's. Oh wait, no, that should have been 0, 1, right? Oh no, oh no, 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 -1, 0. Okay, I'm just being dumb right there. Okay. I am being dumb right here. I have this all correct, and I'm like talking myself out of it. So t is -1, so I'm going to get a -1 plus 1. So that says to me 0 equals c e to the -1, and that tells me that c should be equal to 0 for the initial condition -1, 0, which says to me we should be getting the equation y equals t plus 1. So this is awesome. Everything that we saw on the graph that we did by hand and guessed has been completely verified by our computer-generated solution, and we could then go back to verify that our guessed particular solution does indeed come out from solving the computer-generated solution with the initial condition that we originally used. So lots of, I'm kind of like beating this to death right here, but like I'm trying to like tie together like the 18 different ways that we're coming at exactly the same thing here, kind of letting you see if this is all closely interrelated and that our guesses are good. Remember that making guesses is a good thing for you to be doing this semester. Okay. So one of our two technology goals is to hopefully be able to use technology to find solutions to differential equations. We just did that. We helped ourselves out with some particular solutions. By the way, maybe a thing that you want to go do is say, can you figure out how to make SymPy produce particular solutions for you? It's absolutely the case that in SymPy, you can also give it initial conditions, and it will use those to give you particular solutions rather than the general solution that we found over there. Maybe that's something that you should Google around for on your own right there. The other thing we want to be able to do is have technology produce these slope fields for us. I hope that the most aggravating part of this video so far has been filling out this table right here. It was for me. At least drawing this was kind of satisfying because I was like starting to like imagine the curves emerging from the little pieces of line I was drawing. Making this table, that's dumb. I hate tables. Tables are the worst part of all of math for me. So I don't want to do that. So what we want to do is use technology to do this for us. Now, a very exciting thing happened a couple of weeks ago, which is that Adobe Flash experienced its like end of life. It's like not a thing anymore. So you like can't download it and get it on your computer unless you do like weird things, like your computer doesn't want Adobe Flash anymore. Unfortunately for us, the technology that I've been using as my essential grapher for like every time I've taught this class in the past, last 3 times I've taught this class, it is fully dependent on Adobe Flash. Also, actually, I forgot. I do have a little story about this one right here that I'll show you guys in 1 second. So the cool thing is that this D field P plane programs that I've been using in the past, they were actually in part written, these pieces of software in part written by the person that I replaced when I was hired at College of the Redwoods. Dave Arnold was a person who taught at College of the Redwoods for like 40 years. Coincidentally, I actually went to graduate school with his daughter in Montana, and he is like this dude isn't just some college math professor. He is like a prolific writer. In fact, he's written a differential equations textbook. He also wrote some algebra and trigonometry textbooks. He's written software that is associated with these textbooks. He's written like thousands and thousands of lines of Mathematica code to help produce all this stuff right here. He was an epic dude. And he was actually partially responsible for creating the programs that I've been using that have been like publicly and freely available for years and stuff like that. Because he's a baller like that. So good job, Dave Arnold. I'm sorry that I am a mere human compared to Dave. You don't get Dave, you only get me. And I'm trying to use his code and I can't anymore because that died a couple weeks ago with Adobe Flash. So the point is, we get to use different technology this semester than I've used in the past because that's the way it is. So in my fantasy, we would just be using Desmos because Desmos is honestly one of the best like math tools that's been created in the last couple of years, in my opinion. It's free, it's super easy, but Desmos just doesn't do lots of like higher level stuff that I really want it to be able to do. Yeah, friendly cat, I appreciate the sentiment right there. Good. I appreciate you bringing that Twitch culture into my statements here. So unfortunately, Desmos is not super hot for doing crazy fancy stuff. As all you guys know, there's a million math nerds on this earth that are into putting in a ton of legwork to force complicated things to happen in simple situations. And that has happened in Desmos. So Desmos does not have some nice built-in function that does this for us, but some nerd put in a huge amount of legwork to force Desmos to do this for us. So technically it exists. So if you do a Google search for Desmos slope field, the first hit will take you to exactly this thing. I included the link right here. So let's go take a look at what this looks like. Let's go take a look at exactly our situation, right? dy dt equals y minus t. Let's see what it does here for us. So I'm going to control click on this guy, take us over to Desmos, pop back over into the browser over here, and it's going to bring us up this grid right here. So it looks just like a slope field. This is very satisfying to me. You can see that we get an equation that's over here. It's in terms of x and y instead of t and y. That's no big deal to us. We can handle that. Desmos really likes particularly x and y as its variables here. It doesn't like being shaken out of that. So I'm going to get rid of their equation and their given slope field here. And I'm going to do ours, which was y minus t, which I will call here y minus x. And hey, I hope this looks a lot to you like the slope field that we produced a bit ago. So pros and cons to this thing. The thing I hate the most about this is this. It's stuck. This thing right here, there's like a folder of like a crap load of like every single one of these lines had to be individually written. So the slope grid is just this gigantic list of just crap loads of points out there, which is a kind of a bummer for us right there. So it's not extended further. Like you can't just zoom out further and get more, which is kind of a bummer. The other thing that's a pretty big bummer here is that I can't like click on this thing and get it to produce for me an individual curve. So that's also a bummer. The nice thing about this is that we do get an individual point, and so you can drag this point around, and I know it's hard to see on your screens, but what's happening is that this point also has a line associated with it, so this would help you see some like intermediary slopes that are between a couple of lines that aren't already on there. There we go, now it's actually better. And so actually really cool that you can see the slope change at any location of the trajectory of that particular solution that's right there. So this little tool right here is maybe really helpful for you being convinced that we are going to have solutions that asymptotically approach this linear solution from both sides, that's going to sort of act as like a barrier between a bunch of these solutions in the lower right that are going to dip down towards negative infinity and a bunch of the solutions in the upper left that are going to tend up towards positive infinity right there. So pros and cons to this thing, it kind of sucks because you can't expand. Like if you wanted to look somewhere else, you can't. This like lives in a negative 10 to 10 grid, and unless you wanted to like go into the slope grid code over here, which I definitely don't. You can't do that. And I really want to see what the particular solutions look like. And this doesn't seem to have any way to graph those for me. So bit of a bummer, but if you just love Desmos, then great. Then there exists a Desmos thing that we can technically use here. So it's option number one. I kind of think it's the worst one, but I do like people like forcing this stuff into Desmos. And again, my like fantasy is that I'm going to like wake up one morning and Desmos is going to be like, we've created a whole calculus applet or something like that. And then I'm going to freak out and it's going to be awesome. And nobody's ever going to use a TI calculator ever again. It's going to be great. That hasn't happened yet, but I'm keeping my fingers crossed. I like Desmos enough that I'm happy that this exists, even though I don't recommend it as your grapher for this semester for your slope fields. So back to our document here. It's good because it's simple. It's bad because it's simple. That's sort of what I have to say about this. I want to be able to plot particular solutions. I can't do that. It's not terrible, not my primary recommendation. The better solution here is CalcPlot 3D. If any of you guys have taken a class with Steve Jackson at College of the Redwoods, then you have seen CalcPlot 3D and probably every single day of the class. He's a massive fan of it. I am a ever so slightly smaller fan of it, but I still love it. This is sort of like what I wish Desmos was like, but for calculus-based stuff and for 3D stuff. This is an awesome tool. I think this is just made by some like random dude or maybe some small team of dudes at Monroe Community College in New York. For all the calculus classes you're taking for the rest of your life, this should probably be the thing that you're using for all of your calculus related needs. It does a ton of super cool stuff and it does a lot of stuff in 3D. To find this, I always just Google for CalcPlot 3D because it's sort of at some like kind of weird website. It's not just like desmos.com. That's easy. Importantly, and actually, let's do this real quick because I want to show you guys. I'm going to say this paragraph and then I'll show you both versions. CalcPlot 3D as a standalone thing is really like a 3D grapher. We're looking for a 2D grapher of some calculus concepts here. So it turns out that the slope field generator is actually like a different applet, so we'll actually have to get there from a different place. I do want to just briefly show you guys CalcPlot 3D, and then we'll also look at, and so you can see C3D, that's CalcPlot 3D to them. And this is the direction field grapher. A direction field and a slope field are the same thing. It's just two different names for the same thing right there. So let's check out CalcPlot 3D in general, but then particularly the part of it that we actually care about right here. So again, I'm going to control click on this guy right here, or you can just do, CalcPlot 3D slope field and it'll take you there. Even though it's called direction field there, it knows to look for slope field also. So coming over here. So this is what it takes me to, and okay, let's look at this one first real quick here. So this one you can clearly see, very importantly, sticking arrows on the end here to see what the direction of motion is that we're experiencing at any point in space out there. So for our differential equation, it gives us dy dx, and we can go ahead and plop in our expression here. In fact, notice this one at least gives us the convenience that we can change the variable as we want to here. So I'm going to change our independent variable to t, and actually it updated that for me. That was kind of cool. And I'm going to make this y minus t, and I'm going to hit enter. And hey, so we've got the same picture again right here. The extra cool thing that we can do with CalcPlot 3D is I can just click on this thing and oh goodness, that's not good right there. So does that look to you like a solution that should be passing through this thing? Why or why not? I think that the answer is no, because I know that every single line here should be like a line of tangency to a solution. And I can see that these lines are like, there's lines that are like perpendicular to this dang thing right here. It actually agrees with it down here, but I think that's just because of a coincidence. So here's our dilemma. CalcPlot 3D doesn't have the ability to actually formulate the general solution. It's just holding over this incorrect general solution from the previous differential equation that was sitting here in the box. So when I'm graphing this thing, it's graphing the particular solution according to this wrong family of functions. So it doesn't know it. So notice one thing that kind of is a bummer about CalcPlot 3D is unless you can come up with the general solution, it can't actually graph particular solutions, which is kind of the whole thing I want in the first place here. But the good news for us is we've already used Python to come up with it. So let's go ahead and enter in that solution that we got. We got the solution of c e to the t plus t plus 1. So I'm going to give it that solution. It now knows this guy right here. Notice it plopped down the one very important solution for us already. And now when wait a minute, why is it still giving me incorrect curves out here? Wait a minute, what is this line? That's strange. Okay. I don't quite know what it was graphing. But the bottom line is now that I've typed in the general solution that's actually going to work out for us here, now I can drag this slider bar around and see what the different coefficients of c on that exponential term are going to do for us. And we can see, as we saw before, that c equals 0 ends up being associated with that. Oh, come on, do it for me, you jerk. Ends up being associated with that linear one right there. It seems like all the negative c's are going to cause us to have a decaying exponential, and all the positive c's are going to cause us to have exponential growth right there, which is pretty cool right there. Yes, okay, so it sounds like you've had Jackson in the chat right there. He couldn't live without CalcPlot 3D, especially now that we're all online. And now that we're saying that, though, I want all of you to stop and do a super important mental exercise for yourself right now. Stop and think about taking this class 30 years ago. What in the world would you do? We're so dependent on having technology help us with this stuff, like cripplingly so. You should recognize that this study of differential equations has been really, really, really difficult for hundreds of years. And it very recently has become a much more accessible topic because, like, it used to take an hour to produce this, and now we can produce this in literally seconds, right? Think about how much by hand work went into this. Absolute mountains. That sort of ended once we finally got nice computer systems to do this. I think you're completely correct, Friendly Cat. I think crying would be the appropriate response to having to do any of this stuff by hand, right? So, like, just stop and think about this. Like, really think about the people that came before you. And I don't care if you are like excited. Okay, I care if you're excited about this or not. It's crazy to me that you would even make it into this class if this kind of thing didn't excite you. But really stop and think about taking this class in 1970 and how wildly, wildly different this would be to figure this stuff out. We're going to be so dependent on graphs and technology this semester. I don't know how I could cover even more than like 10% of this content if I didn't have technology producing this stuff for me. The discipline of differential equations has changed drastically. So many more people are capable of learning this content now because all of the brute force legwork can be done for you so that you can just be the critical thinker instead of the menial labor doer of, producing slope fields and stuff by hand. Like, so really think about the people that came before you and say out loud, dang, I'm lucky to be taking this class in 2021, which otherwise I don't think is a phrase that people would necessarily associate with this. But think of the people that came before you and stop and say, okay, I am the lucky one right now because you are. Otherwise, we'd be doing this by hand here. So super cool. So again, I really like this, but I do want to state my one complaint here. My one complaint is I want to graph like 40 of these curves all at once, and this does not seem to be okay with doing that. Maybe if some of you guys are better at CalcPlot 3D than me, you could show me how, but I don't really see how to do that here. And I want lots of these all at one time. So this still kind of bothers me. I just want to be able to like click and gosh, I don't know what it's trying to graph right there. What in the heck? There's got to be some equation that it's graphing that I don't know about. Anyway, so that's still my one shortcoming of this. And by the way, I did want to go ahead and Google some CalcPlot 3D for you guys here. So let's go ahead and do that. So just going to general old CalcPlot 3D, you can see it's at this monroecc.edu. That's the college of the guy that made it right here. In general, CalcPlot 3D is for making really nice 3D graphs of things. And I mean, already, if you haven't seen this before, I'm assuming you're saying, holy crap right now. And this thing can do so much cool stuff. It can put tangent planes on this. It can, there's a ton of awesome things that you can do. Vector fields, space curves, lines in space, parametric equations. You can do stuff in polar. You can do it in Cartesian. You can do it in cylindrical. An unbelievable amount of things. Like this is like Desmos for adults right here. It's pretty epic. It doesn't do some things like automatically like solving for important locations. Like, how Desmos will tell you like X and Y intercepts and like solutions on a graph and stuff like that. This one doesn't do that as well. But this is impressive enough for me. So CalcPlot 3D does do a bunch of great stuff. We're not interested in the like actual CalcPlot 3D. We're going to be interested in using the slope field generator or the direction field generator all semester. But just be aware that this exists. Like for any 3D modeling, any calculus stuff you're doing in the future, this is the technology you should be using to help yourself visualize it. So even if you don't use this website for this class, this should come up for you in your life later. This is a very powerful thing that mathematicians have been desperate for years, and apparently just a nerd at Monroe Community College did it for us. So thank you, dude, at Monroe Community College. You are a true hero. So what a great guy. So those are our options out there for us. There is one more now that I've found. So we kind of identified our graphical solutions right there with greater than 0. We increased. Those were the ones that were up here. Equal. Oh, sorry, I'm gonna switch back over here. I had said here greater than 0. Those were our ones that curved up. Equal to 0 is our straight line. Less than 0 for C was all the ones that bent down right there. Yeah, no kidding. Somebody should be giving that guy an award, and I feel like it should be Jackson and all the other people that appreciate it so much right there. I mean, I don't know. And again, think about taking Calc 3 and not having that grapher available. I just don't know what you would do. Visualizing that stuff has to be crazy. Oh yeah, I forgot. I'm going to do story time after I show you. I'll just do it right here. So here's story time. So our book right here, differential equations, right? So I'm flipping through this book, and I know that what some of you guys have seen is that this actually comes with a CD. There is actually a slope field plotter on this CD right here. So if yours did come with a CD, and if you have a CD drive, which I literally don't on my computer, you could use this as an alternate source right here. And I want to show you this. And so, by the way, when I took both Calc 3 and differential equations as an undergrad, there were no graphical, no technology components in that class. We just sort of covered other topics that weren't so heavily dependent on technology, right? So I took these at St. Louis University when I was like 18 and 19 years old, about, whatever, 15, 14, something years ago like that, right? And I took both those classes with the same guy, Calc 3 and differential equations, when I was like freshman, sophomore at St. Louis University, right? Not one computer-generated image was ever brought up in either Calc 3 or differential equations for me when I took it. When I started to use this textbook then, as a professor, right, 4 years ago, I was reading through it, just like the introductory stuff at the very beginning of the book, and I'm scanning through this thing, and I look down at one point. Where'd it go? Oh, there it is right there. And I see at the bottom of the acknowledgements page, and I know this is flipped for you guys, but whatever. At the very bottom of the acknowledgements page, I'm flipping through this book, and I look down and I'm like, I know that name. And it says, we are also grateful to John Cantwell, the guy that was my professor for Calc 3 and Diff Q of St. Louis University, where I went to college, for his thoughtful and insightful suggestions, as well as his help with some of the logic for the software illustrations. What the crap? I took the class with him, and he apparently is responsible for writing the code to produce all the images in this book. What happened there? So I at least think that's cool. There's a shout out to my old professor that's in our differential equations book, but I'm mad at him because it was apparently for making all the nice computer generated images that I never saw when I was his student. So, dang you, John Cantwell. I wish I saw those graphs when I was taking this class. I know, I can't get away. He's following me around here. So I do want to show you guys one more option right here that's slightly better, but I don't know. CalcPlot 3D should become your friend. I think that's good. So I did some more Googling, and basically all I did was just, Google like slope field grapher, and I found this was like the 6th or 7th option. And I think that this is one of the better ones that I've found. Bluffton, I don't know, that's a college somewhere, and some nerd has also made this thing here. I like that the word nerd is sort of in the thing right there. I think that's supposed to be somebody's last name. But if it is a last name as a mathematician, then that guy won the lottery right there for nerd names. And so let's take a look at this one real quick here. Wait, don't highlight. Click it. There we go. So go into this guy here, and we'll switch back over. So this one here, you can see some similar type stuff. This can handle doing one ordinary differential equation. This is also going to be useful for us later this semester because we are going to be spending like half of our semester talking about systems of differential equations. So that's going to be in there. There's some polar things that are in here. And by the way, you guys will be getting so there's nothing in polar coordinates, I don't think, in our entire textbook. One piece of the like Tony created content this semester is going to be a little bit of stuff on polar differential equations and graphing them. And as a exciting thing, this will sort of help you, but sort of not, because I'm going to make them hard enough that this thing can't handle this stuff right here. So look forward to that right there. Oh my gosh, no, it has polar systems. Is this going to ruin everything for me? Oh man, is this going to ruin my assignment? Oh, I didn't even realize it had polar systems. Well, crap. Well, maybe this won't be so cool. Anyway, all right. So just pretend you never saw that. In any event, we want to go to 1ODE right over here. Type in the things we've been seeing. I've got y minus x because it wants x's and y's instead of t's and y's. We're back to the same image. But the thing that I feel better about is I want to plot numerical solution curves. And so the cool thing is that you can either just click and generate a new one, right? Which is highly satisfying to me. I want to see the families of curves out there. This is sort of like filling in all the gaps between the lines. This is really giving me a better sense of flow rather than just direction. So now it's much easier for me to describe the general behavior of any initial condition at any point. By the way, notice that you can conveniently just clear all the ones that you've done. And also, if you want a very special initial condition, like if you wanted 2.5 and like -1 as an initial condition, you can just type in that point and it will go to -2.5 and positive 2.5 and -1. And that's exactly sitting like right there. So you can see that this is the curve that does go through that particular initial condition. So you can either just click for generic ones or you can manually enter in the specific one right there. I should point out to you that this is asking you in a drop-down menu. It just says the word Euler, and I'm sure that doesn't mean anything to you yet. Oh, crap, it does. Okay. So just because of the way that my thing is set up right now, this actually does create a drop-down menu. You just can't see it because of the way that I'm sharing my display right now. But it does give several other options that, again, they're underneath my mouse. You just can't see them right now. Our numerical unit of this class is going to be talking about the different ways that these curves are computed. Like, how does a computer do this if it's not symbolically solving the differential equation, right? We still want to be able to numerically estimate what these solution curves are going to look like. This is using Euler's method currently, but we are going to look at some other methods. The improved Euler method and the Runge-Kutta method are going to be some other methods that we're going to use here. So when we do our little 2 weeks on numerical solutions, estimating what a solution curve looks like, but without solving the differential equation, we're going to write some code, and Euler's method is going to be the thing that we start with. In fact, Euler's method is actually section 1.4 of this class. We're in section 1.3 right now. We're skipping 1.4 just because I want to lump together all the numerical stuff at once, so we're going to wait till chapter 2. But then we'll talk about some other things. So this is asking what technique do you want it to use to make the computations? And by right now, the default is Euler. There's smarter ones to use. This is actually the lamest one, but these curves all do look correct right here to me. So in any event, I think that this one actually, Daryl Nestor right there. Okay. Thank you, Daryl. I appreciate the grapher that you made right here. And so just some cool stuff right here. I kind of think that this is right now currently our best available thing right here. So maybe this bluffton.edu one. It looks to me to be the one that seems the most useful. If you find one that's better, then you should share that. But this does what I want. I want to be able to plot lots of particular solutions simultaneously, and this allows me to do that. So that's why I like this one a little bit better than the CalcPlot 3D one, and a lot better than the Desmos one. But ultimately, this is very equivalent to the one that I was using in the past that is now defunct. So there we go. And again, this is going to keep on being what we want. We're going to talk single ODEs for a while. We're going to talk systems in chapter 3 and 4, basically. I'm going to introduce my own content on Polar, and you guys are unfortunately going to be able to cheat and look up your answers with this thing right here. Whatever, we'll do that when we get to it. So let's pop back over and kind of wrap our things up right here. The technology takeaway. There is no one nice, neat little package that does every single thing that we want. Well, there is one. It's called Mathematica. It costs $166 per person. Don't buy that unless you have a really good reason to. Mathematica is awesome. It's just a little too expensive, but I get it. They have a whole team of PhDs making that stuff. Like, it's not simple to make things really, really good. Can I make it a 3x3? What window are you talking about making bigger? Are you talking about back over here? Are you talking about like the bounds on this window? I think that the presets down here do that. No, apparently not. Functions. Oh, it's going to be, how do we do that? Oh, here's our bounds right there for our window. That's right there, -4 to 4, -3 to 3. So I think that you can adjust your bounds of your window right there if we wanted. We could make this thing way broader. And yeah, that just expands the thing right there. And now we're much more spread out. But you should notice immediately, notice that this thing is really struggling to draw the particular solution curves because we zoomed out so much more. We're going to very specifically talk about why that just happened right there once we talk about our numerical stuff. And even better, if you can see, that looks just like one straight line and then a light kink right there, and then another straight line. We're going to see exactly this behavior. When we go to write our own code to do this, we will see this type of stuff happen and see kind of how to fix that stuff right there. So if this is stressing you out, don't worry too. And we can see it. But again, if you can see that dark purple one, it's a bunch of straight line pieces that are being attached to each other, not a smooth curve. We're going to see exactly this type of behavior in a few weeks when we do our numerical unit right there. So if these things do funky things to you, oh, there we go. There's those hard corners right there. We'll be reproducing this and fixing this. And by the way, you can actually fix this over here. I'm sure that will, there we go. That fixed it right there. Smaller breakdown. That h is exactly the h from your limit definition of the derivative right there. That's saying how far do you want me to go before I recalculate my derivative. Here I just said only go a tenth as far before you stop and adjust your trajectory again right there, which is why that changed. In any event, so you can modify this thing right there, which is good. So our technology takeaway, Mathematica would actually be the one best package for all this, but it's really expensive, so don't buy that. We have some free resources for this. Another thing to note is that we are going to make our own solution grapher in Python. We're going to make something that not only numerically estimates solutions, but also creates the plots of those particular solutions. And we're going to see the techniques that are used to do that, the algorithms that do the numerical estimates for these things. Ours are going to be slightly less fancy than the things that are going to end up getting used in some of these solvers because, as you might imagine, some of these techniques get kind of advanced for predicting the trajectories of these curves out there. But we're going to look at least two, perhaps a third technique and there's like probably at least a dozen different algorithms for producing these curves. We'll look at a few of them, but it'll be ours, and it will help us to understand what are the underlying like you should just be saying to yourself, like, what computation is that grapher doing to produce those things, given that it isn't coming up with an equation? It's only coming up with an estimate of what the graph should look like, skipping over the actual solving the differential equation part. So like, what computation is it doing under the hood? So we'll understand that here in a few weeks of how those graphs are getting generated. And again, we're going to produce we won't be producing a slope field because that's kind of a pain in the ass to make hundreds of little lines like there, but we will be producing our own particular solution graphs like that. And that'll be pretty satisfying for us, both in one and two, or like one-dimensional and two-dimensional differential equations out there, second orders as well. So I do have one last example that I still do want to talk through one example here to talk through a little bit more slope field stuff, but I do think I'm going to skip the last example that I had for the day just because it's not super duper exciting. So I do want to do this example and I'll call it a video since this kind of went a little bit long, but I'm glad that I talked a ton about the technology because you guys do need to sort of just play around with it and get comfortable with it. And kind of the bottom line is this section 1.3 is sort of get comfortable with your technology. It's all about graphs and you don't want to make the graphs by hand. So like you need to be able to do the graphs technologically. So that's the bottom line there. So let's talk about some special cases and we'll call it a day. And I'm going to kind of chop off my final example here. It's in the book anyway. You're good. So there's two special cases that we sort of want to acknowledge here. They're the ones that we talked about last class, which is that for any general ordinary differential equation, there could be t's and y's on the other side, but the special cases are where there's only t's on the other side, and the other special case is when there's only y's on the other side. The fact that this equation has no y in it and this one has no t in it makes it easier for us to analyze, easier for us to make broad statements about what the graphs are going to look like, stuff like that. So in the case where we have no y dependence on the right-hand side, only t dependence, then that means that the rate of change of y, right, the rate of change of y, dy dt, only depends on t, like time, right? That means that as the value of y changes, that doesn't necessarily change what our slope of y is, right? Only changing time affects the rate of change of y. So what does this mean for all of our slope fields with ordinary differential equations where there's only t stuff on the right-hand side? Well, what it means to me is that changing the value of y does not change the slope. So I'm going to draw my little example of this then. So what that means to me is that there should be things on our slope field then that look like a column where, for example, changing the value of y, as y changes, The slope is constant, right? Changing y did not affect the slope. Now, what I know with this differential equation right here is that it should be the case, right? I'm going to kind of do my quick little graph right here. Notice that if t is 0, we get all slopes of 0. Notice that if t is 1, we get all slopes of 2. If t is 2, we get all slopes of 4. And now I'm going to go the other way. If t is negative 1, we get all slopes of negative 2. If t is negative 2, we get all slopes of negative 4, etc., etc. What shape does it seem like we're shaping up inside of here? Looks to me like all those particular solutions look somewhat parabolic. And oh, what do you know? That's actually the case right here, right? Integral dy equals integral 2t dt. Oh, what do you know? Y equals t squared plus c. Of course, that's what we're going to get right there, right? We just integrated, and it matches that the slope field example exactly right there, right? So the point here is this. If there's no y's, then changing y doesn't change your slope. So moving up or down, you should have exactly the same slopes all the time. So what that means is that every column is exactly the same. Or excuse me, sorry, I said that sort of, I meant to say the right thing. Every slope in a column is the same slope. Each individual column is going to be different, but the slopes within that column are all the exact same. So it seems to me like in this case, we could have just drawn one row of slopes because like notice here that every row is the same, right? The bottom row of slope lines is the same as the second, same as the third, same as the fourth. Each of those rows matches because each slope line in a column is exactly the same because there's no dependence on y. So we should see the opposite behavior then when we look at our second example here. In the case where there's only y's on the right-hand side, the rate of change of y depends only on the value of y. Changing time won't change your rate of change. Only changing the value of y will change your rate of change. That means that the changes in time t do not affect the rate of change y. It doesn't matter if y is 6 now or if y is 6 in a million years. It's going to be changing at the same rate, right? So what does this mean for slope fields with dy dt equals f of y? Well, let's go ahead and try and graph a slope field for this, right? So let's say I want to analyze this particular differential equation right here. I hope that you guys are on board with the fact right away that although this is clearly separable because it only contains y, you probably can't do this thing, right? You would need to be able to integrate e to the negative 0.1 y squared times sine squared of y. Or times 1 over sine squared of y. Even worse right there, right? There is no way that any of you or any human can do that integration. So what I know is I cannot get an explicit analytic solution for this thing by hand. There's no way to do it. It's not like we haven't covered the technique yet. It's that you have the technique. It's separable. It's just that the integration isn't physically possible, right? But that doesn't mean we can't analyze this differential equation and long-term trends of individual solutions and saying, if we have an initial condition of 0, 2, then what happens to that thing in the long term? Let's just state that as our goal right here. Let's just say, right? So again, I might want to know about the long-term behavior of a particular solution, saying if my y value started at time 0 being 2, if y starts at 2, what's going to happen to y in the long run? Is it going to get bigger? Is it going to get smaller? Is it going to go to positive or negative infinity? Is it going to converge on a value? I don't know. We want to know what happens to y in the long run. Well, one way we could do this is if we could solve the differential equation, get a y equals equation, I could just take the limit as t goes to infinity and answer it. But I can't because I can't solve this thing. So I can't do the limit route to find the long-term behavior. So instead, let's see if we can go ahead and draw this differential equation graph right here. So the question I'm getting right now is, if a human can't do it, does that mean it doesn't exist or that it exists in a different mathematical language? I do suppose that kind of what sometimes happens in math is that when we arrive at something like an integral that is not integrable, then occasionally what mathematicians will do is just define that as its own quantity. And there's lots and lots of these in math where we just define something. And one good example is like our normal distribution. It's e to the negative x squared. Well, there is no antiderivative for that. So when we talk about in statistics the area underneath the normal curve, we just say, yeah, what's the function for the area underneath the normal curve? Instead of actually saying the equation, people are just like, well, yeah, it's the integral of the normal curve. And they define it as such rather than actually computing it. And often it's the case where it's so common that we need to use numerical techniques to compute these integrals anyway, that this is not a rare case right there. So I suppose that it's possible in some of these cases that we might, in a sense, invent a new representation of something that allows us to then represent the quantity. But I don't. I shouldn't make guesses about which of these that's potentially possible with and which it can't. What I can tell you is that there are classes of equations where mathematicians are able to prove that there can't possibly exist a closed form solution to an integral. But that's not all of them out there. But what you'll find when I'm sure that all of you are going to be responsible and go to graduate school for math, a lot of your time will be spent proving statements rather than solving things, graphing things. A lot of it will be saying, can we know something for sure about all things of this category, right? So proving that something is true. And one of those big things that's out there is like proving, can we prove that a certain family of equations can't have solutions or are guaranteed to have solutions, but they can't be expressed in closed form, or, right? All those different possibilities that are out there. And so what you're asking about certainly belongs in its entire field of mathematics, which is what equations are solvable is the more general question that we're asking. And I hope that you're not terribly surprised to hear that there are dozens of graduate level courses that you could take, graduate level textbooks, and about a bajillion and a half Stack Exchange mathematics posts discussing these types of things that are out there, right? But currently, this is known as a non-integrable function. There does not exist a closed form function, a y equals function, that will ever be the antiderivative of this thing based on the current system of algebra that we use to describe things. So that's my roundabout